Thanks everyone for joining, and welcome to my talk, Bridging the Gap from Data Science to Production. Yeah, a few words about myself. I'm actually by profession a mathematician, so I got a mathematical background and thus joined like from the data science side into the actual industry. And I worked mostly with the Python data stack. And one of the fields I'm really interested in is causal inference and uncertainty quantification. And of course, data science to production, which means for me that whatever I want to do should also be somehow useful in the end. So should make some value in business. As it was already mentioned, so we are inovex, we are an IT project house, we have a focus on digital transformation. So AI and data engineering is one big aspect, but also the whole portfolio. So we want to have this end to end, and thus we can even provide from product discovery, so really early on, everything to like application development, data science, data engineer, also if it has an UI or UX on web, mobile, wherever, also where you operate this, like IT and operation, and also training. This is like the whole stack, the whole portfolio, and this is really important for us to be not only focused on AI, so not only a company that does proof of concept, but to provide everything also so that it can go to production. Yeah, and this is already the starting point for this talk. So this talk basically originated from my own experiences and all the discussions I had with lots of people over the last, let's say, 9 years, because this is about the number of years where I went from the university into industry as a data scientist and actually learned that data engineering is actually the most important thing to bring things into production and to actually get some value out of it. And we're going to touch now different aspects, different facets of this as laid out here. And we're going to start with the use case. So if we look at the use case, and this might be really, really individual, depending on the use case and on the requirements, if you really look down on this from a high level perspective, you can maybe identify 3 components. And I think it's important to be really early on aware of those 3 components and what they are in your specific use case. So we have the data, we have the model, and the model is some kind of transformation in a way, and we have some kind of results. And now let's take a look into those different components. So depending on your use case, you might get your original data from some kind of database, some distributed file system, or maybe it's rather a stream, but you should really care early on how is your data actually accessed in the end. And I mean in a production way. So it's not enough if someone like gives you some CSV snapshot of some data and lets you work on it. So you should really ask early on in a use case, well, after now having this snapshot, how are we gonna later access the new data, because data, of course, always changes. And then you should ask questions like, depending on your use case, is it rather batch oriented? Is it enough to get new data once a day? Or is it maybe rather a real-time use case and you have to react on some events on a web page, or stream-based, maybe IoT? This is something really important to find out early on and also to note. And then, of course, the model. This is like in a data product, in some data-driven service. This is where everyone kind of focuses on. And when I'm talking about the model, I'm not only talking about the machine learning algorithm, like a random forest or some artificial neural network. For me, the model includes everything, like everything from the interface where you got your data from to, in the end, the results. Because in the end, it's some kind of transformation that also includes all the pre-processing steps you do, cleansing, imputation, scaling, all the construction of the derived features, in the end, this is part of your model, and it's also something that you have to bring into production, that you have to deploy eventually. And so if you're working in a Jupyter notebook, you do all the kind of things, be aware that in the end, this needs to somehow be scalable in a production environment. So yeah, ask the question yourself, are you working on raw data or some pre-generated feature? Where really is your interface to the original data? Maybe this is provided by some other department, and speak about this. What is the interface we can rely on? What is the schema on some table? It can be, depending on use case, many different things, but this is important to state early on. Talking about state, it's also important to ask yourself if your model really is some kind of mathematical function in a way, so that you just put in some input features and you get some results, or if it has some state, maybe you're using LSTMs or whatever, and in a streaming context, and you're keeping some state. This might be problematic in the end if you're going to scale out, or if you need to restart your model in a production environment. Also, this is something to note down. And most often, the simpler you go, the better, especially later in production. Let's take a look at the results. Yeah, the results may vary depending on your use case, but also here it's important to talk about the interface. So who are the actual users of your results? Is it just some insights you generate, maybe for the marketing department, and it's enough to put those results into some database, some distributed file system? Do you have to stream something on Kafka maybe as a new topic? Or is it rather that your use case demands some web service so that maybe some clients can ask for the results on demand? All this is important to understand really early on, and to talk about and to the users of your results. Also here, the frequency and recency is really important. I mean, if you do demand forecasting, for instance, and once a day is enough, and then maybe it's also not important if it comes 1 hour too late. But if it's a real-time requirement, then it's important to be really, really fast. So from a high-level perspective, again, if you look at this, we have those 3 components. And in the end, we want to kind of deploy the model. And I've already talked a lot about those interfaces that you need to specify early on, maybe by talking to other departments who actually are responsible for the initial data sources, or to a department then that kind of act on top of your results and provide some web service, or maybe you provide it, but it's important to think in the terms of interfaces. Then if you look at all this, it's interesting to make some kind of taxonomy or some characteristics of your data use cases. And here, this is just an example that you kind of think about if your use case is, as I said, rather the stream-based, or that you deliver your results by just writing into a database, which makes it much more simpler. What kind of problem class you're dealing with. It's also going to be really important for production to see what volume and velocity of data you're dealing with. If your prediction is batch, near real time, or real time. And also really important is the technical conditions. Maybe you're working together with a company that has a still strong Java stack, and everything needs to somehow incorporate it in the way that it's going to run on some application server, or maybe it's everything in the cloud and you just need to provide some Docker containers. But this is something that needs to be clarified early on. And also here, it's like there's no one size fits all. So depending on the use case, your architecture eventually might look really different. So the main takeaways from this kind of use case perspective is state the requirements of your data use case, identify and check data sources really early on, define the interfaces with other teams, with other departments. And what's even the best is if you test the whole data flow from input to output early on, maybe with a dummy model that you really just write something that reads the data, writes it back into another database where the user is going to grab the results later just to see if everything technically works. Because as it turns out, in many projects, people concentrate totally on the machine learning model at first for, let's say, half a year. And then they think, OK, let's deploy this in a week. And then they realize that there are a lot of technical issues they could have foreseen, but they just did tackle them way too late. We've already talked a lot about interfaces to other teams, to other departments. And this, for me, was one of the things I really had to learn, that organization and team handling is really important. Because in the end, we want to have some really fast process of iteration, because your data product is not a one shot. Whatever you do, it's going to need to be iteratively improved. And there's the crisp, the AMP. I think everyone learns about this at the university. It's like really old, I think from end of 90s by IBM, the cross industry standard process for data mining. And it defines this that you start with the business understanding, then you go to data understanding, data preparation, modeling, and evaluation. And what many people do, they go directly from the evaluation to business understanding again and never really do the deployment. And or only then when really the deadline of the project is really near. And my take on this is that you really have to do deployment early on to see that something is working end to end. And also, I think that deployment also helps your business understanding, because the earlier users in your use case actually use the results of your data product, the earlier you get feedback, and feedback helps you with the business understanding. So just like on some just like on some CSV file, like generating a model, evaluating, improving the model, it really will not help you that much with business understanding. What helps you is to get the first simple model running, get the feedback of the users, and then you understand if you're really optimizing for the right metric, for the right KPI. And there it helps a lot what already helped in the development of general software products, actually. So this is not specific to data products. This is just common sense. Meanwhile, that it's really bad to have a clear separation of developer teams and operation teams, and developers only care for certain aspects like code releases, and then they have some release and they throw this release over the so-called wall of confusion, and operation just has to deal with it. And this kind of makes the process of iteration really hard, because whatever you throw at this wall, you don't really see what happens to this, and people on the other side don't really understand what it is. So really early on, this gets you into a kind of wrong cultural thinking, in the sense that one team thinks, okay, this is not my job. That's deploying is job of another team, and but I made a great model, and they did something wrong in the deployment. And what you need to go to is that you have teams caring for everything end to end, and that they really want to make a great data product. And it's the responsible then of the whole team, and the responsibility should not be shared. And what the actual solution to this is the DevOps culture, which is meanwhile also like really matured. And they say that you need continuous delivery. So meaning you have teams that are continuously able to deliver and deploy states of the current development, and to test easily and to have everything nicely automated, monitored, and so on. And to transfer this now into to the context of deploying and developing some kind of data product. So my experience is I've also worked in teams at the beginning, in teams where only data scientists really tried to make the best model possible, of course, and you concentrated only on the model. And we always struggled a lot to get anything into production. And so my recommendation is, and also what I've seen and experienced like firsthand, when we kind of changed the team setups, that we have heterogeneous teams composed of data engineers, software engineers, and data scientists, and even a data product manager, someone for UI, UX. And if you have the responsibility for like the whole data product and not just for some machine learning model, then everything got much smoother, and actually results are possible, and putting things into production is possible. And like a rule of thumb for me was that for one data scientist, you even need 2 to 3 data engineers. So actually there's much more need for data engineering in this use case, but we're also going to see this later on too. You might have heard about Spotify, how they do it. They have even kind of brought this to the extreme in a way. They say they have fully autonomous team with the end-to-end responsibility for even each feature. And this is a really interesting approach. I pointed out the URL, and I think you're going to later also get the slides shared. So this is an interesting article to read if you don't know him. From my experience, I have to say I've never actually experienced this firsthand to have it like in Spotify, but I think it's definitely a right direction to have this heterogeneous teams and have the responsibility end-to-end as much as possible. Now let's talk about a bit more technical things. So the languages. I mean, in the end, we're going to program something, right? And there, if you want to do something in productions, you're going to realize early on that you have a 2-language problem. So you have on the one hand, you have the industry, and the industry is quite often Java stack based. Also Scala is one of the languages, strongly typed languages, and of course they emphasize robustness and also want to handle edge cases, because in the end it's about running a business, and things should not just break down because someone mixed up some data type. On the other hand, in many data products, if you talk to the data scientists, they really like prototyping languages like Python and R, something dynamic type. They rather put their emphasis on is there a good ecosystem with some fancy methods and results, and as long as it runs somehow on their machine, they are fine. And in some kind of data product, you have those 2 worlds if you want to bring something into production. And now we're going to see what kind of ways and methods you can actually do to solve this problem, to overcome the 2-language problem. Of course, you can say, yeah, let's just select one language, for instance, Java. And this then helps you, of course, deployment is going to be much easier if you are anyway on a Java JVM stack. And if also your data scientists work with Java, but then, of course, you're losing the whole ecosystem. You're abandoning the wonderful Python or R data science ecosystem. And this might be, a really bad choice, especially, since you then have to reprogram things that are just available in Python, for instance. I mean, there are some companies, I know that Netflix did this at the beginning. I think they also changed to Python. But choosing one language is one way. So let's look at Python. So nowadays, quite often, Also, Python is just used in production. That's especially useful in my experience for batch prediction use cases, because you then don't have such strong time constraints. You can also do web services with Flask. Everything is possible. You can horizontally scale during a prediction. And you can, of course, tap into your databases or your data sources with things like PySpark. It's quite well developed. And especially if you use Python or your whole model, then in the end, if you deploy it as an isolated container, this might be a way to go, especially for batch use cases. But this is also something that needs to be checked depending on the use case and the company, if the infrastructure is ready for this. Then I've seen actually in some projects where people tried a different solution. So they said, okay, let's have the data scientist program in Python and R. And in the end, if the model looks good, we just reprogram everything more nicely in Java or Scala, and then we move it to production. And this is really, for me, it was, I've seen this a few times, a worst case scenario, because if you later have a bug in production, you don't know if it's due to something that was wrongly converted from Python to Java, or maybe it's a systematical bug already in the original code. So you never really know. And it's also hard to iterate on your data product. So we've talked about the iterations. If you want to move fast, then this really slows you down, because you then are in production in Java, and everything that is done then is in Python, and you always have this huge conversion step. Another thing is that people sometimes try this with some kind of exchangeable formats. And there is some of them like PMML, ONNX, and PFA. So they really look great in theory, I have to admit, but I've never seen it actually working. They have a quite limited functionality and flexibility. We've also already talked about the fact that a real model is not only the machine learning algorithm, it's the whole thing, also the pre-processing. And most of the time, like I think ONNX, there you have all the nice machine learning algorithms in it, but you can't really express all the pre-processing step that your model needs. And so you're missing a huge part of what you want to, in the end, bring into production. So this is something from my experience, something I would not recommend to use. Another solution are frameworks. I mean, there are some of them. I mean, you could see that TensorFlow is a framework. You can access this with Java, C, C++, Python, R. There's H2O. And this we actually applied in some projects, so that data scientists could work even with R and build H2O models. And in the end, the model was exported as Mojo and then ran on a Java server. But there we also had to take care of the pre-processing on two different sides, so one in R and one in Java. So, but in this use case, there was not that much pre-processing, so it was possible. But this is using a framework that has several languages, several bindings, is definitely a way to go. What it costs you is, of course, the flexibility, because then in the end you can only use what H2O has to offer, for instance. But in practice, it can also help with deployment quite well. So take a small recap at this point. So if we look at the three major solutions that were presented, like to re-implement, to use frameworks, or to just use a single language. My recommendation is to definitely never ever go the way of re-implementing whatever data scientists do in another language. Either go with a framework, or if you go with a single language approach, then definitely go with Python, because yeah, compared to R, it's much easier to bring Python into production. Yeah, mostly than using Docker containers and so on. So let's now talk a bit about quality assurance, also a thing that might not be, or where data scientists might not be that familiar with, just coming from a more scientific background, and also something I really had to learn the hard way, is that in your now heterogeneous team, you should really stress the point that everyone does clean coding, that you use certain software design patterns, that you write really good code. And clean code for me means code that is easy to understand and easy to change, that you have nicely structured code. And this is important to get the awareness of this in the team. So it's not something you can just post to people or just demand in a way. You have really to convince people clean coding is going to help you later on, and helps you to do the iterations that we have talked about, because you're going to read your code more often than you actually going to write it. Another thing is that I've seen quite often in Python, people don't really do Python packaging, proper versioning, and so on. And there are tools that do this. So one of the tools that I also worked on is Scaffold. And it's also important to in teams to kind of help with the setup, to as a team to decide, okay, let's have, for instance, some pre-commit hooks that we have, for instance, some standards like black, or that we run our unit tests before we actually commit, and that our code are proper packages we can then more easily share and distribute in a company. Another aspect is definitely monitoring. So I was once in a project, this was like really early on, where we had something in production, and then there were some iterations. So the machine learning model was improved, and it was improved on some test set we just deployed, and the results in production were actually quite bad. So yeah, we were definitely lacking monitoring at that point. And my takeaway was from this point on that you should definitely, like, monitoring should be the first thing you do when you go into production. Measure your KPIs, what is important to you. Could be something like a click-through rate or conversion in, let's say, a recommend a use case. And quite often those KPIs are also a bit different to whatever you optimize on in your machine learning algorithm. But KPIs are the things that are important for business. So keep track of them. Also track of like technical things. How many requests do you have in your service maybe that provides some model? What are the timeout delays? This is really important to measure all the time, because if you have, for instance, a new recommender model that is working in real time, so on each new event or click, you get other recommenders. If there's the timeout or delay too high, then the whole experience on the website might be really, really bad. And all this, even though it has not that much to do with machine learning, it's still important for the overall data product. And thus it's important to keep in mind. So there's also one really nice book called Site Reliability Engineering by Google. And yeah, I referenced one chapter of it. And there they even see this as a pyramid, and monitoring is the fundament of this. And I must say that I totally agree with this. If you don't monitor whatever you do, it's kind of you're flying blindfolded. And this is something you definitely want to avoid. Talking about quality, also structure and processes, if you have some kind of use case where people start experimenting around and doing different performance optimization or whatever, it's also good to help a team to succeed by providing like frameworks and tools. Like one of I really like is actually Neptune AI, and it's kind of similar to MLflow, which I think many of you might have already used or heard. It's just helping you to track your experience, to track your experiments, and to also compare them. And this allows you to maybe like half a year later look back and see, okay, what were the results like 6 months ago with some different kind set of hyperparameters on some old model. And it helps you to structure your work. And yeah, for me, it's definitely something that needs to be established also early on, because later, if you don't do it and everyone's doing different experiments, different ways of storing those, it's really, it gets messy over time. Another thing, a special monitoring for, let's say, data products in general is that you also, of course, need to measure the quality of your results. And this gets tricky in a production use case, right? I mean, with the test sets, you know your results, but if you run it in production, you might not be, you don't have a test set. You cannot really say if it's really better or worse. Only, but what you can do, you can, for instance, do simple check like a response distribution analysis. So on the upper right side, we see some classification model, and let's say it's classifying between cats and dogs, and cats are left and dogs are right. Only by looking at the distribution, you see that a model that rather returns responses with around 0.5, so around the point where it's not really sure if it's a cat or a dog, that this distribution on the lower right side looks really bad. And having tests on this and some alarm system can help you really much if for some reason your model in production degenerates, and it's better to have some alarm system that tells you there's something wrong than to have angry customers calling you half a day later that nothing works anymore as expected. Another thing is, of course, A/B testing. I stressed several times before that, I mean, doing something on a test set is completely different than doing something in production. So every new model, even if it looks good on a test set, it has to show also in production that it's better than the model before. And that means from a data engineering, from a technical perspective, that your infrastructure should be able to do A/B tests, meaning you have to be able to have several models together in production, and to see if one works better as the other. And this then allows you also to do special things like multi-arm banded approaches, for instance, for A/B testing, to roll out maybe a new model in a really slow way, only by seeing if it really is better than your baseline model. Technically, being able to do A/B tests means that you, of course, have to version your models, and you have to link them to certain user groups. This could be like a recommender use case, for instance, where you split your users in an A and B group, and that you really are able to track the results of a given model up to the point where they are facing the customer. And this might sound easy, but in general, in some grown infrastructure architecture, it might be really tricky to be able to achieve this. Now let's talk about the actual deployment. So let's assume that we have solved all these aforementioned points. Deployment now, I must say, really heavily depends on your chosen approach, on your architecture, on your analysis of the use case. But still, some principles apply. We have talked about this iterative process. That means we want to do continuous delivery. This is something that that your deployment should support, and continuous integration. And continuous integration requires that you work with versions, that you package your stuff, that you have some kind of artifact store, that you have, of course, unit tests. This is also something that is most often forgotten, and that you automate as much as possible, because automation always helps with reducing human errors. And automation also means that you have to embrace processes, because you can only automate things that are defined in a way. And there are tons of tools nowadays that help you to do this, like GitHub Actions or GitLab CI/CDs. There's still old Jenkins, and it's important to establish something like this also already from the beginning, and not like an afterthought after 6 months. Okay, let's start with the continuous integration. Do it right at the project start. Here's a small little example. Also, all the details are in a blog post. We really care a lot about this, about proper engineering and continuous integration. We have seen in some projects that people just use Git clones in some Docker file, and then they ship the Docker file and everything is right. But here is shown that it's much better, instead of cloning directly, that you really go the long way, because it's going to help you in the end, that you build proper Python packages, that you upload them on some artifact store, that you download them again, that you run the unit test, so that you play this whole process through one time. And then you can maybe later on use this to build some virtual environment in your Docker file. But it's much more, it's much cleaner than just cloning your repo, because then you know, okay, which version did we use in Docker, compared to just, okay, what was the Git commit we cloned. And so it's definitely, it looks more complex at first, but it helps you so much more also, that you can just install a certain version easily from your artifact store. Another thing is, this is from an old paper of Scully from 2015, that also stresses again the point that if you do machine learning pipelines, if you do a data product, then the most technical debt is actually not in your ML code. So this is the little black dot in the middle. That's all not where your technical debt is. It's rather in all the things around this, and I highlighted those in red, where I think they are connected to the deployment, like configuration, process management tools, all your serving infrastructure. We've talked about monitoring. And be aware of this, that the most important things, or like 90% or even more of what you do in a data product, is actually engineering. So to highlight the most general principles again, do versioning, packaging, have defined processes and quality management, it definitely helps to have development and production environments as similar as possible. So working with pandas the whole time on your own machine, and if you later know that it needs to run in Spark, might not be, or yeah, at least it gives you a huge gap that you somehow have to cross again. So keep it as close as possible, automate as much as possible, and show and try to have everything as isolated and controlled as possible to avoid this it runs on my machine problem. Yeah. Here I also want to point out another great resource. I think it's the Google's best practices for ML engineering. And yeah, I don't want to go through all of them. I think there's also only a little bit of time left. Maybe only the first rule: don't be afraid to launch a product without machine learning is actually one of the best rules ever. So this is what I also mentioned before, like try to get like end to end with some dummy model, because you can later on add machine learning, but starting only with machine learning gets you into trouble if you then later decide to go to production and you realize you have made a model that is not possible to be deployed because it's too complex, and it actually calculates something that no one cares about because business thought of something completely different. So yeah, launch whatever you launch really early on. So this already brings me to a kind of summary of what I've learned over all those years and what my experience are, and I hope that it helped you too a little bit. If you want to bring something to production, it's really depending on your use case. We have seen this kind of taxonomy of different use cases, and it's important to be aware of this early on and design your architecture. Think about quality assurance. Try to have heterogeneous teams. Establish a development DevOps culture with the shared responsibility over the whole team, where everyone tries to go and reach the same goal. To overcome the two-language problem, either go for a single language like Python or choose a framework, and in general try to automate as much as possible, embrace processes, and be aware that production definitely is not an afterthought. Right from the start, do this. And there I think that data engineering is really extremely important, and it's becoming more and more important. And also to stress this, yesterday evening, I just tried to Google for jobs, data scientist and data engineering, and actually the hits, it's like 6 times more demand for data engineering than data scientists, and that's actually also what we see in the demand of the industry. So data engineering definitely is a really cool domain to be in right now. And we are also looking for new data engineers. So if you're interested, drop me a line. And yeah, thanks for your attention.